What's going on, everyone? My name is Johnny Bandon, and I'm your CCNA instructor for this CCNA video series. And in this video, we're finally going to tackle configuring OSPF. So we just went through a very long lecture about OSPF, or what I feel is very long, right? More than 30 minutes. Woo! Got to take little breaks here and there, right? But now we're going to get into the fun stuff, configuring OSPF. And we start that in our CCNA studies with just a simple lab here. So if we look at just the layout, right? We got two networks sitting over here on R2's LAN, two networks sitting over here on R1's LAN, and it's our job to make sure that these PCs can talk to each other. We do that by enabling OSPF, so R1 and R2 can share their link state databases, right? The networks they know about, and we can begin to actually have dynamic routing and have full convergence of our small little network here. So again, for our paid viewers, this EVE-NG topology is available to you as long as you click on our central repo link. All of our EVE-NG labs are available to you and already pre-configured, meaning R1 and R2, the only things we have to do is configure OSPF, make sure that we do the right network commands and actually enable OSPF correctly, and we should be good to go. For our non-paid viewers, if you're watching this on YouTube, we do have a Git lab here with all the instructions. We have baselines that you can paste in. We also have the solutions for the lab. So you can go and actually look at the solutions, right? What you need to configure to get the lab to work. So with that being said, let's go ahead and get started. I'm going to bring my Git lab over here to the right on a monitor you guys can't see, and that's where my instructions are going to be. So as you can see here, I already have all my devices powered on. So step 1, power on all devices. And then step 2 says paste baseline from GitLab, which we've already done if you're part of our paid course. Now, as you can see here, I've already done some configuration on these devices prior, right? Starting this video. So I'll just get that out of the way because we're here just to focus on OSPF. So the next step is to verify all IP addressing. And really what this means, guys, is let's just go and make sure that everything is configured correctly before we enable OSPF. And we do this because since we're focused on the OSPF technology, we don't want to worry about things that we should already have configured, right? So if OSPF isn't working, it's not some wrong access VLAN not connected here on PC 6, right? So that's the reason this PC can't ping PC 8 over here. We want to make sure just all of our baseline is done, okay? So on switch 1, we're going to do some verification. We're just going to type in show VLAN brief. Okay, VLAN 10 is in the right port. VLAN 20 is in the right port. We're going to make sure our trunk is good. Yep, our trunk is good to R1. And then R1, we're going to make sure that, let me expand the secure CRT a little bit, right? Okay, so ETH00, and again, I'm looking at my network diagram over here on the other monitor, guys. I don't just memorize this, even though I do create the labs. But ETH00 has the right IP address, and then we see our two sub interfaces. That should be good to go. If we just take a look at these here, they are configured correctly. Awesome. We're going to do the same thing on R2, show IP interface brief. And this is also good to go as far as IP addressing. And then we'll take a look at our sub interfaces just to make sure that we are configured correctly. Awesome. Now switch 2, we're going to do the same command, show VLAN brief. So interface 00 should be on VLAN 10 and interface 01 should be on VLAN 20. And then of course, let's check our trunks. Awesome. So let me just start my pen application up here, guys, because before we start configuring OSPF, let's go over what we need to know, right? Or kind of let's get our bearings. So if we take a look at our network here. Okay, give me 1 second. If we take a look at our network here. So R1 and R2 need to be sharing what they know, what's on their LAN, what's local and connected to them. So when we go and configure OSPF on R1 and R2, on R2, we're going to need 3 network statements because we have to advertise this network here because that's a network. And we have to advertise this network and this network. And then on R1, we're going to do the exact same thing. So really, this should be pretty simple. It's actually going to be like 4 commands total, and then we can see OSPF come up. And then from there, we can do a lot of our verifications, our Wireshark captures, right? And really kind of dive into the OSPF packets, okay? So let's go ahead and do that. So on R1, we're going to go into global configuration mode. We're going to type in router OSPF and then a process ID, which again is locally significant. So it can be router OSPF 1 over here on R1, and R2, it could be router OSPF 69, right? In here, we're going to set a router ID. This isn't part of the instructions, but I just want to show you how to set it statically. And as we remember from our lecture, if we didn't set this statically, it'd go off the highest loopback. And if we don't have a loopback, which we don't, it goes off the highest active interface with the highest IP address. Okay, so it'd be this if we didn't set the router ID statically here. And now let's go ahead and do our network statements. So this network statement, this is going to enable any interface that matches this network that I'm about to specify to be a part of that link state advertisements. So this network command is identifying, okay, hey, this is the network that we need to advertise and put in our link state updates, right? So there's a couple different ways we can do this, guys. I mean, really, the network command syntax is always the same. It's going to be network and then an IP address and then the wildcard mask. R1 here. What's our subnet mask? It's a /31. The network address for that network is 10.10.10.0. So we'll do 0.0.0.1. So essentially the inverse, the wildcard mask is the inverse of the subnet mask, right? And this is because it's identifying specifically host bits here, okay? And then we have one more thing that we must do when configuring OSPF, and that is set the area, right? Because all routers have to be in some way connected to that backbone area. So we're going to make this area 0. And since CCNA just wants you to know about single area configuration, for all of our OSPF labs that are required, it's always going to be area 0. Boom, and it's that easy. Now let's go ahead and advertise our other networks that are connected to us. So as you can see here, the wildcard mask is going to be 0.0.0.255, and that's because the subnet mask of this network is a /24. So the inverse, right? 0.0.255. Then real easy here, we're just going to up arrow, and boom. That's it. We're done here, guys. Real easy, real simple. Now let's go into R2. We're also going to create our router instance, our OSPF instance here with the locally significant process ID. We'll set the router ID just because we want to, right? Just for fun. And now let me show you something. Something else you can do with this network command is actually just put a host address in here. So we can actually just do something like this. Instead of specifying the network and the wildcard mask of the network, we can just go ahead and put the actual IP address that's on this interface for our network command and just do a /32 wildcard mask, which is the inverse of all 255s, or a host address is what we call that. And this will also work for advertising that network. And as you can see here, we already come up. We have this syslog message saying, hey, we are in a full state now. So what that means essentially, we are on a broadcast OSPF network, and we have just synchronized the OSPF link state databases for now. We're about to add some more network commands that are going to enable reconvergence, right? Because OSPF only sends periodic updates when there's been a change in the topology. And right now, OSPF believes we're fully converged. And when we type in this command, we should see a change in OSPF. Not that we should go back to the two-way state, but essentially if we were looking at this on the wire, we would see those LSAs be advertised now. into our topology. Awesome. So now let's do some show commands, guys. So if we're going off the instructions, it says to verify OSPF neighbors. So we do that with this command here, show IP OSPF neighbor. And boom, would you look at this? We can see here our neighbor 1.1.1.1. We're in a full state. We can see the OSPF priority of our neighbor. So the default, which is a 1. We see our dead timer, which again goes up to 40 seconds. If you don't receive a hello within 40 seconds, we come down. We see the neighbor's address and the interface of the neighbor. And we see that we are we should be the designated router. Let's go ahead and check what R1 thinks, right? So IP OSPF neighbors. Okay, awesome. So it's saying that it's the designated router. So it's saying that R1 is a designated router. But we know that if all priorities are the same, the highest router ID should take over as the DR. So what we're going to do here, guys, is we're going to go ahead and force this OSPF to reset and do the hello state again. Let's see what we got for our OSPF neighbors. So essentially what happens here, guys, is since R1 was configured first, it made itself the DR, right? And in that election, it didn't go in the right sequence and order. So R1 probably already sent the bit on the actual wire. I think it's like an M bit or an X bit, and we'll break it down in the Wireshark capture that says, hey, I'm the designated router. But when we actually cleared that OSPF process and now they send their OSPF hello packets at the same time, we see OSPF functioning as it should according to the RFC, right? Where if the OSPF priority is default and equal, the higher router ID should become the designated router, which we have now. So kind of cool when we lab it up, we kind of learned this about OSPF, right? That depending how you configure it in the sequence, right? Since R1 was configured first, it made itself the DR, right? And we can actually go ahead and look at that Wireshark capture, right? Of the hello process and how they become neighbors, the topology table, and then full synchronization. Okay. Next show command it wants us to do is verify OSPF interfaces. So that command is show IP OSPF interface. And this is going to show you all the interfaces participating in OSPF. And you got a lot of good information here. So I'm just going to cut it off. Let's see. Include Ethernet 00. Actually, I'm sure we can specify. Yep, ETH00. And let's just go ahead and look at this output. As we can see here, we got our internet address. We can see the network type, which is broadcast. Pretty cool, right? So we can actually see with this command that we are part of a broadcast network, which tells us that we will have a DR and BDR, and that our hello timers are going to be 10, and our dead timers will be 40. It also tells us information about the DR and BDR. So pretty cool. Okay, another command here is show IP OSPF interface brief, which will just show us all the OSPF interfaces with a brief output. So it's funny that it says here that ETH03, its sub interfaces are the DR. Well, of course they are because there's nothing on the other end creating an OSPF neighbor. However, these are participating in OSPF because their networks are being advertised into the link state database, into that topology table. Now, there is a way where we can turn off the hello packets from leaving these interfaces, and we'll probably get into that in the next, actually in our bonus labs, because learning about passive interfaces isn't part of the CCNA exam, but it is possible to have this output just say the interface that's making that OSPF neighbor. Okay, next, verify the OSPF learned routes are in the routing table. So that's going to be show IP route. And this will show us everything. But if we do show IP route OSPF, we just see our OSPF learned routes. Now, why isn't this direct connection in there? Well, that's because you have that locally, right? So it's not going to show you that you learned about the 10-10-10 network from R2 because you know about that network locally, right? So even though we're advertising it or we make a network statement for that network, we still just receive in our routing table the OSPF learned routes that we didn't already know about locally connected. So in R1's perspective, we learned about R2's LAN networks down here. Okay, and then verify the LSA types in the link state database. So this command can be show IP OSPF database. As you can see here, we have type 1 and type 2 LSAs being advertised and created. And that's because we're only working in area 0. If we decide to add an extra area here, then we would have type 3 LSAs being advertised into us from our ABRs or our area border routers. So pretty cool. Okay, next step. Perform a Wireshark capture and reset the links. So what we're going to do here is come into R1. We're going to go into interface 00. We're going to shut that bad boy. We're going to minimize this. And we're going to perform a capture on 00 so we can actually take a look at that OSPF process forming, right? The neighbor table, topology table, everything. So actually, I'm going to go ahead and pause this video, guys, because I just created a new EVNG instance and I need to get Wireshark working. So I'm actually going to pause this. Stay tuned for part 2 where we get into Wireshark. Okay, we're back. So if you guys are wondering what I did while I paused the video there, what I had to do was essentially open up PuTTY and SSH to my ESXi. Actually, SSH to the EVNG server IP address here, which I'm running on ESXi. Before, I was using just VMware Player on my local computer, but as my labs get more complex, I actually invested in some physical hardware. So a Dell PowerEdge R910 with like 128 gigabits or megabits, gigabits of RAM, and then 40 cores of CPU. So I had to go into PuTTY and actually SSH into it so that it saved the SSH keys or the RSA keys, which Wireshark needs to perform the TCP dump in order to perform that capture. Something kind of like an EVNG-ism, right? So now we can do our capture on R1. And then we can come back to R1, go into interface 00. You can see this hello packet. And let me just go ahead and zoom in. This hello packet we can see coming from R2 with that 224.00.5 multicast destination. That destination address is the OSPF all routers address. We can see our header here where it's telling us no authentication. This is a hello packet. This is part of the backbone area. And the hello packet, we can see our network mask, right? We can see we're saying we're the designated router. And then in this section, we can just see TLVs, right? Extra options. So, okay. So now let's go ahead and no shut interface 00 on R1 and let's see the fireworks. So as this interface comes up, OSPF hello packets are going to be sent. And then we see everything, right? We see our neighbors be formed in these two hello packets right here, right here, and right here. As you can see, it turns into unicast, right? Once we receive a reply to the hello packet. And then now we start sending our database descriptions here between R1 and R2. And here we're deciding, right? Okay, we know who the DR BDR is. Now let's figure out what's on my link state request list. And then we're going to, let's see here. R1 is going to send request. And we're going to send request updates and acknowledgements back and forth until our link state databases are fully converged. So if we just take a look into these hello packets here. So this is coming from R1. Let me just fully expand this. So R1, this is saying that we don't know the designated or backup designated router yet. So here's my priority. Here is my router ID, right? And then we see router 2 respond saying, here's my router ID. And then I am the designated router. That's what it's telling R1, saying, hey, I should be the designated router because, again, my router ID is higher. And then this last hello packet is going to get sent out via multicast, essentially saying the same things. And then we have R1 here sending its database description to R2. We can see here that OSPF header saying it's the source, saying we're in the backbone area, no authentication again. And we're going to send things that need to match, right? So our MTU is 1500. In that database description, we have these bits that need to be set. And this allows us to kind of get that synchronization, right? And then we have R2 sending it back. And then we see we keep sending these database descriptions. And then in this database descriptions, these two here, we're actually going to send LSAs saying, hey, here's what I know about. Here's the LSAs I have. Right? And now we're going to build that linked state request list. So R2 is going to do the same thing back. And since R1 is not the designated router, it's going to send LSA request saying, hey, I'm requesting to know about all the LSAs in the network. R2 is going to update it. And then it's going to request saying, hey, did you acknowledge? And then we just see updates sent back and forth until our acknowledgement's here. So really the important thing to know here is just kind of the flow of everything though, right? So hello packets are sent, neighbor table is built, and then we send our database description packets. In these database description packets, we're going to tell the other side, hey, here's our master-slave relationship. Here's what I need to know about. And then we start sending our requests and our updates. As you can see here, the BDR R1 sending a request to the DR, and the DR sending an update back. And then we see them sending updates back to each other of the networks they know about until we send that LSA acknowledgement. And pretty cool here, you can see how they go from unicast to multicast. Until that final update coming from R2 and that final acknowledgement. Then once we get that final LSA acknowledgement, we can assume that the link state databases are going to be fully synchronized. And then we run that OSPF algorithm, shortest path first algorithm, right? To place those routes into the routing table. So now if we head back to our routers, go ahead and run that command, show IP OSPF neighbor again. And as we can see, this time again, it did do the right thing and made R2 the designated router, which we saw in our Wireshark capture here, it actually happening on the wire. All right. So last thing we got to do is just ensure reachability between users. So that's too easy. We're just going to go to PC5 here, and we're going to ping 192.168.10.1. We can reach it. And now let's make sure we can ping the actual PC. And we can. We have full reachability. We come back down here to our Wireshark capture. We should have seen those ICMP messages getting sent back and forth. And the process in that, right, is once that packet gets sent to R1, R1's going to look at the destination IP, see that it's destined to 192.168.10.5. It's going to check its routing table to see if it knows about that network, and then send that packet on its way to the next hop. Okay, sweet. So that is going to be it for this lab. Actually, let me show you one last thing. I just want to show you the routing table again. And just show you the administrative distance and the cost right here, okay? So the link cost is 10 for these Ethernet ports. So when we learn about 192.168.10, this is a cost of 10 right here, and then this is a cost of 10. And that's why it equals 20 when it gets to R1. Sweet. So now that is the last thing I wanted to show you guys. I hope this video was informative. Sorry about that break I had to take. I like to have videos just flow, but that's okay. And thank you for viewing, and stay tuned for our next lab. We're going to go over some advanced stuff, and I hope I don't make it too long. So thank you.